This is video 2 in module 2 on nomenclature and related concepts. Some of the related concepts really go back to analyzing structures of organic molecules. So we start here with degrees of unsaturation or unsaturations. And what this refers to is typically rings, molecules that are in the form of rings, or double or triple bonds. And for an unknown compound, you can determine the number of unsaturations from the molecular formula. So here we have a molecular formula. And if we apply the equation above to this formula, we see that if we have 20 carbons minus hydrogens over 2, so that's 13. There are no halogens and no nitrogens, so we can ignore those terms, but then there's the plus 1 at the end that we need. So 20 minus 13 is 7, plus 1 means that this molecule, whatever it is, has 8 unsaturations. That's just an example. Typically, you would only use this formula for an unknown compound. For which you have the molecular formula. Usually we get that from a technique called mass spectrometry. You may also use it just as a check if you just want to check to make sure you have the right number of unsaturations. But usually we look at the number of unsaturations just by looking at the structure of the molecule for a known molecule. More about unsaturations. So really, when we're talking about a saturated molecule, it means that it is saturated with hydrogens, meaning it has the most hydrogens it can bear. So if we have a carbon framework and all the bonds are filled out with hydrogens, it's a saturated molecule. To get an unsaturation like a double bond or a ring, you have to remove 2 hydrogens. Notice, if I remove these 2 hydrogens, then each of the carbons needs an additional bond, and that bond results in the double bond. Notice the formula has 2 less unsaturations. So to go from ethane to ethene, the alkene, as we name them, is the loss of 2 hydrogens. But also notice, for the molecule propane, to create a ring also requires the removal of 2 hydrogens. If we remove these 2 hydrogens, then each of these 2 carbons can have another bond, and we can have cyclopropane. So back to our nomenclature, cyclo is simply put in front when we have a ring. Cyclopropane, cyclobutane, cyclopentane, for example. So we're doing nomenclature too as we go along. I have some cyclopentanes drawn here. And more about structure, bonding, and isomers, if you recall. So cis and trans are terms used for certain kinds of isomers. And it's best used on rings, but it can also be used in alkenes. So for example, if we have this ring, and I'm going to draw a methyl group, okay? Hopefully everyone sees why this is a methyl group. There's a CH3 at this position, but it's implied if I don't draw that in. So even the end of a line, the end of a wedge, or the end of a hash mark still represents an implied carbon with its hydrogen. So here's another methyl group. These 2 are cis to each other. Okay, so this is technically speaking cis 1,2-dimethyl cyclopentane. If I draw them both going back away from us, this is also cis, but Now, in fact, if you realize and build the models for these, which is highly recommended, if you flip this like a pancake, you will get these two and notice that they're the same. So in fact, there is only one version of cis 1,2-dimethylcyclopentane. However, if I draw one up and one down and switch that over here, one down, one up, now if you flip it, they no longer overlap. They no longer superimpose. These are different. And we're going to get into the more complex naming of those kinds of molecules later. But this is just to point out that this is trans and that this is another molecule that's also trans. We're going to hold off on the detailed naming of these types particularly for now. Alkenes can also be cis and trans. Notice methyl group here, methyl group here. If I fill in implied hydrogens here and here, it might make it easier to see. Methyl, methyl. So these two methyls, referring to the methyls, are on opposite sides. So this is a trans alkene, and this is a cis alkene. Notice these are on the same side. Okay, so that's the concept of cis and trans, along with some other naming stuff in there. So we can take all this information together in the solving of a problem like this. For example, how many isomers of C5H10 are there? If you were to apply the formula above, you would find out that there's one unsaturation. So I can draw, the way I like to approach these problems initially is, okay, 5 carbons, 1, 2, 3, 4, 5. And connect those. And then if I fill in the numbers of hydrogens, 1, 2, 3, 4, 5, 6, 7, and I only have to add 3 more, so 8, 9, 10 actually. And then here's my one unsaturation as a double bond. So another way, but I really wouldn't normally draw it all like that. To be honest, I would do this to begin with. So it might take some practice, but you want to get to this point. So we have an alkene. There's our one unsaturation in the form of a double bond. Now, to figure out how many isomers there are, I would put the double bond in a different place. So that's a different molecule for sure. And then I just above pointed out cis and trans on alkenes. So this molecule can have cis and trans, I just realized. So here's the double bond, and now I'm going to point this down like this. Okay, so this is trans at the double bond, and this is cis, and those are different molecules. And part of this goes back to structure and bonding. So you cannot rotate around a double bond. There's an X there, okay? So double bonds are fixed in space. They're trigonal planar, they're sp2. You can't rotate around the double bond because you would have to break that pi bond. If you can go back and visualize that, you would have to break the pi bond, then rotate around the single bond, and then reform the pi bond. So that's not easy to do. So these are two different molecules, trans and cis. You'll want to avoid pitfalls like this one, saying, for example, that this is another one. No, it's not. Because if you flip like a pancake, you will see quickly that that is the same as that one. So this is not another separate one. Right now we just have 1, 2, 3. There are no other places to put a double bond like this, but there are certainly other ways to draw a molecule like this with a double bond with 5 carbons. This is all we're really asked. So there's a double bond, 1, 2, 3 carbons, 4, 5 carbons. right? There's another structural or constitutional isomer of this molecule. I'm probably not going to draw every single isomer of this. You can try to draw others that I didn't think of, but I do want to point out that, remember, again, above, an unsaturation can be a ring. So a cyclopentane has 5 carbons and 10 hydrogens, and so that's another isomer of this molecule, of this formula. Yet another is a 4-membered ring with a methyl group sticking off of it. And you can fill in the implied hydrogens on this to convince yourself that this is true. And we can go on and on like this. There's actually quite a lot of isomers of this. You can build models to convince yourself that things are different. I would build them anyway just to get used to seeing how molecules look in 3D. If I draw a 3-membered ring with a methyl pointing up and a methyl pointing down, that's 5 carbons. And just like the example above, I can draw down and up, and these are different, just like the ones above were different that I showed you that were trans. So these are both trans. And then of course there's a cis version of this. So look at all the isomers. So even a very simple formula like C5H10 could mean a whole bunch of different compounds, which is pretty cool. I like these kind of problems because they reinforce structure and bonding, they reinforce geometry, they remind us that of things like rotation around bonds, like for example, if you look at this bond right here, if I rotate around this bond, I can redraw the molecule like this, but and that would tell me that these are the same, right? So just rotating around a single bond doesn't change the molecule. What changes the molecule is having to detach and rearrange and switch bonds and move atoms around. And then just to conclude that thought, just remember that you can't rotate around double bonds. There's no rotation around the bonds of rings, but the bonds of rings do sort of flex. If you build the model, you'll see that, but flexing does not change cis, trans, geometry, or anything like that. Okay, so that's the end of video 2.